We have a tutorial to look at Newton's laws of motion and Newton's law of universal gravitation together. Amongst other common misconceptions with the law of universal gravitation, which isn't that big a deal at this level of trying to understand astronomy, but I do want to point out that in astronomy we're going to have a lot of cases where there's an inverse square law, and people don't quite have the same intuition for things that vary as the square of a factor, in this case the square of a distance. We're better at thinking about things that are linear. And so not so much for the law of gravity, but the intensity of light coming from an object, the apparent brightness of an object is also following an inverse square law. And that's going to be more important for us later on in the class. So I'm going to spend some time talking about Newton's law of universal gravitation. I also wanted to point out that it's not an accident that the electrical force between two charges follows an inverse square law. The law of universal gravitation, the attractive force between two masses, follows an inverse square law. And the way that the apparent brightness of a light falls off with an inverse square law as well. And those are all consequences of living in a three-dimensional universe, three spatial dimensions. All right, so part one, the force of gravity. Newton's law of universal gravitation describes the attractive gravitational force that exists between any two bodies with the following equation. So we have the force of gravity is equal to G times m, big M times little m, divided by the distance squared. G is the gravitational constant, or Newton's constant for gravitation. For the point of this tutorial, we just take big G to be 1. Big M and little m are the masses of the two objects attracting one another, and r is the distance from the center of one object to the center of the other object. Given that Earth is much larger and more massive than the Moon, how does the strength of the gravitational force that the Moon exerts on the Earth compare to the gravitational force that Earth exerts on the Moon? Explain your reasoning. Before we go into answering that, let's consider our two students and their thoughts on this. Consider the following debate between two students about their answers to the previous question. Student 1, I thought that whenever one object exerts a force on a second object, the second object also exerts a force that is equal in strength but in the opposite direction. So even though Earth is bigger and more massive than the Moon, they still pull on each other with a gravitational force of the same strength, just in different directions. Student 2 says, I disagree. I said that the Earth exerts the stronger force because it is way bigger than the Moon. Because its mass is bigger, the gravitational force Earth exerts has to be bigger too. I think you are confusing Newton's third law with the law of gravity. Do you agree or disagree with either or both of the students? Explain your reasoning. So I'm definitely going to disagree with student 2. All of Newton's laws are true. You can't pick that one is true and the other is not in this context. That's why they're laws. They're not opinions. They are laws of nature. So every force obeys Newton's third law. And if you look at the structure for the strength of the gravitational force, it's just the product of the masses. One of these is the mass of the Earth, the other is the mass of the Moon, and it doesn't matter which order I multiply them in. I get the same result, because multiplication commutes. So, same strength, and y, the force of gravity, is proportional to the product of the masses. It doesn't matter what order you multiply them in. So, agree. disagree with student 2? I don't think student 1 said anything that was incorrect. Student 2 is missing out on Newton's third law being always true. All right. How would the strength of the force between the moon and the earth change if the mass of the moon were somehow made 2 times greater than its actual mass? So we go back to our form for the strength of the force of gravity. If I take little m and double it, so I double the right hand side, the left hand side is also going to have to double. So strength of the force of gravity doubles. Part 2, so this is where we get into the distance dependence of the force of gravity. In the picture below, there's a space probe traveling from Earth to Mars, and it's at the halfway point. And sort of obviously, this is not a ginormous space probe, so the drawing is not to scale. On the diagram, clearly label the location where the space probe would be when the gravitational force by Earth on the space probe is strongest. Well, the force of gravity is an inverse square law, so Earth's gravitational pull, mass of the space probe is the same, mass of Earth is the same, g is the same. The only thing that's varying is the distance, and it goes as the inverse of the distance squared. So the largest force is going to be when I have the smallest distance. So the space probe is there on Earth when Earth has the strongest pull on it. On the diagram, clearly label the location where the space probe would be when the gravitational force by Mars on the space probe is strongest. Explain your reasoning. So the gravitational pull of Mars on the space probe is big G, mass of Mars times the mass of space probe, so nothing in the numerator is changing, it's only the distance, and I'll get the greatest gravitational pull from Mars when the probe is on top of Mars. Where would the space probe experience the strongest net or total gravitational force exerted on it by Earth and Mars? Explain your reasoning. So I have one force of gravity of the Earth pulling on it, the other force of gravity of Mars pulling on it. Earth has the biggest mass, so the biggest net force is going to be again when the space probe is on Earth. And that's way bigger than when the space probe is out here in space at a large distance away. All right, question 7. When the spacecraft is at the halfway point, how does the strength of the gravitational force on the space probe by Earth compare with the strength of the gravitational force on the space probe by Mars? So we're talking about when it's right here, midway between Earth and Mars. Now let's go to our 2 students and see what they think. Student 1, since the space probe is exactly halfway between Earth and Mars, the strength of the gravitational force would be the same, since the distances are the same. Student 2 says, you're right that the distances are the same, but you're forgetting about mass. The combined mass of the space probe and Earth is much bigger than the combined mass of the space probe and Mars. So, since the distances are the same, the strength of the gravitational force on the space probe by Earth has to be bigger than the strength of the gravitational force on the space probe by Mars. And again, do we agree or disagree with either or both of the students? All right, so student 1 is incorrect. Distances are the same, but that's only one factor in the gravitational force. And so student 2 is right about mass also playing a role, but we need to be a little bit careful about that. It's this word combined, and that is not the way the force of gravity goes. I think when you would think of the word combined with masses, that you would add them together. That is not the case. What is true is that the force of gravity is big G, and then the product of the masses over the distance squared. So I would say student 2 mostly correct, in that Earth having a larger mass is going to have a larger force at the same distance as compared to Mars. But it's trying to be careful with that word combined. It is not added together, it's product, which maybe that's what you think of when you think of combined. I think most people would think, I'm going to combine 2 and 3, and you would say 5, not 6. All right, so we can go back to question 7. Force due to Earth is stronger than Y, more mass. All right. I think a little bit about the motion resulting from these forces. If the space probe had lost all ability to control its motion and was sitting at rest at the midpoint between Earth and Mars, would the spacecraft stay at the midpoint, or would it start to move? If you think it stays at the midpoint, explain why it would not move. If you think it would move, then a lot of stuff to do. A, describe the direction it would move. B, describe if it would speed up or slow down. C, describe how the net or total force on the space probe would change during the motion. And D, identify when, where the space probe would experience the greatest acceleration. So here, what's going to guide us is that we're looking at the force is equal to mass times acceleration. Newton's second law of motion. All right, so previous question on question 7, there was a net force due to Earth when it was at the midpoint. So it can't just stay at the midpoint. There's a force acting on it. Therefore, there has to be an acceleration. So let's go through and answer all these. What direction would it move? Back to Earth. So it would fall back to Earth. Describe if it would speed up or slow down. It is going to speed up. It's going to go faster and faster and faster because it's continuously accelerating in that same direction. And in fact, the acceleration is going to get stronger the closer it gets to Earth. Describe how the net or total force in the space probe would change during its motion. The net force grows stronger. It's inverse square law in distance. Identify when, where the space probe would experience the greatest acceleration, and that would be right before hitting Earth. Gravitational acceleration. All right, question 10. Imagine that you need to completely stop the motion of the space probe and have it remain at rest while you perform a shutdown and restart procedure. So unfortunately, you have to reboot your space probe. You have decided that the best place to carry out this procedure would be at the position where the net or total gravitational force on the space probe by Mars and Earth would be 0. On the diagram, label the location where you would perform this procedure. Where you want to make your best guess, but there's no need to perform any calculations here. It's a little bit of algebra, it's actually not too hard, but we can just talk about it qualitatively, not quantitatively. So let's go back to our diagram. At the halfway point, there's still a force of gravity pulling it towards Earth that's stronger than the force pulling it towards Mars, because the masses aren't equal for Earth and Mars. So where does the space probe have to be? I'm going to have to trade off the smaller mass for Mars with a smaller distance away from Mars. So it's going to have to be somewhere closer to Mars, but along that same line separating Earth to Mars. So I'm going to say it's about there. So closer to Mars. All right. Your weight on Earth is simply the gravitational force between you and Earth. Would your weight be more, less, or the same on Mars? Explain your reasoning. It is going to be less. If we go back to our expression for the strength of the force of gravity, so I've got constant, that doesn't change. M is now the mass of Mars. Little m is your mass. Your mass isn't changing whether you're on Earth or on Mars. And then r is going to be the distance from the center of Mars to you. And even though Mars is a smaller planet, r is smaller. You have a bigger effect from the mass of Mars being smaller, so your weight is going to be less.